China has the quantum technology to perfectly encrypt useful signals over distances far vaster than anyone has ever accomplished, spanning Europe and Asia, according to a stunning new research letter. Bits of information, or signals, pass through people's houses, the skies overhead and the flesh of human bodies every second of every day. They're television signals and radio, as well as private phone calls and data files. Some of these signals are public, but most are private, encrypted with long strings of numbers known, presumably, only to the senders and receivers. Those keys are powerful enough to keep the secrets of modern society, flirty text messages, bank account numbers and the passwords to covert databases. But they're brittle. A sufficiently determined person, wielding a sufficiently powerful computer, could break them. Historically, every advance in cryptography has been defeated by advances in cracking technology. Jianwei Pan, a researcher at the University of Science and Technology of China, an author on this research letter, wrote in an email. Quantum key distribution ends this battle. Quantum keys are long strings of numbers, keys for opening encrypted files just like the ones used in modern computers, but they're encoded in the physical states of quantum particles. That means they are protected, not only by the limits of computers, but the laws of physics. Quantum keys cannot be copied. They can encrypt transmissions between otherwise classical computers. And no one can steal them. A law of quantum mechanics states that once a subatomic particle is observed, poof, it's altered, without alerting the sender and receiver to the dirty trick. And now, according to a new letter due for publication today, January 19, in the journal Physical Review Letters, quantum keys can travel via satellite, encrypting messages sent between cities thousands of miles apart. The researchers quantum encrypted images by encoding them as strings of numbers based on the quantum states of photons and sent them across distances of up to 4,722 miles, 7,600 kilometers, between Beijing and Vienna, shattering the previous record of 251 miles, 404 kilometers, also set in China. Then, for good measure, on September 29, 2017, they held a 75-minute video conference between researchers in the two cities, also encrypted via quantum key. This video conference was announced previously, but the full details of the experiment were reported in this new letter. This long-distance quantum key distribution is yet another achievement of the Chinese satellite Messias, which was responsible for smashing a number of quantum networking records in 2017. Messias is a powerful photon relay and detector. Launched into low Earth orbit in 2016, it uses its fine lasers and detectors to send and receive packets of quantum information, basically, information about the quantum state of a photon across vast stretches of space and atmosphere. Messias is the brightest star in the sky when it is passing over the station, Pan wrote to Live Science. The star is as green as the beacon laser that Messias uses to aim photons at the ground. If there is some dust in the air, you will also see a red light line pointing to the satellite. No sound comes from space. Maybe there are some raised by the movement of the ground station. Just about any time Messias does anything, it blows previous records out of the water. That's because previous quantum networks have relied on passing photons around on the ground, using the air between buildings or fiber optic cables. And there are limits to line of sight on the ground or how far a fiber optic cable will transfer a photon without losing it. In June 2017, Messias researchers announced that they had sent 2 entangled photons to ground stations 745 miles (1,200 kilometers) apart. When a pair of photons gets entangled, they affect each other, even when separated by large distances. A month later, in July, they announced that they had teleported a packet of quantum information 870 miles (1,400 kilometers) from Tibet into orbit, meaning the quantum state of a particle had been beamed directly from a particle on the ground to its twin in space. Both of these achievements were major steps on the road to real-world quantum key encrypted networks. The new letter announces that the theory has been put into action. Messias first encrypted 2 photos, a small image of the Messias satellite itself, then a photo of the early quantum physicist Erwin Schrödinger. Then it encrypted that long video call. No similar active quantum key distribution has ever been achieved over that kind of distance. Already, Pan said, Messias is ready to use to encrypt more important information. Quantum key distribution is essentially a creative application of the so-called Heisenberg's uncertainty principle, one of the foundational principles of quantum mechanics. As Live Science has previously reported, the uncertainty principle states that it's impossible to fully know the quantum state of a particle and, crucially, that in observing part of that state, a detector forever wipes out the other relevant information the particle contains. That principle turns out to be very useful for encoding information. As the Belgian cryptographer Gilles van Ast wrote in his 2006 book Quantum Cryptography and Secret Key Distillation, a sender and receiver can use the quantum states of particles to generate strings of numbers. A computer can then use those strings to encrypt some bit of information, like a video or a text, which it then sends over a classical relay like the internet connection you're using to read this article. But it doesn't send the encryption key over that relay. Instead, it sends those particles across a separate quantum network, Van Ast wrote. In the case of Messias, that means sending photons, one at a time, through the atmosphere. The receiver can then read the quantum states of those photons to determine the quantum key and use that key to decrypt the classical message. Album, the world's most beautiful equations. If anyone else tried to intercept that message, though, they would leave telltale signs, missing packets of the key that never made it to the sender. Of course, no network is perfect, especially not one based on shooting information for individual photos across miles of space. As the Misius researchers wrote, the networks typically loses 1 or 2% of their key on a clear day. But that's well within what Misius and the base station can work together to edit out of the key using some fancy mathematics. Even if an attacker did intercept and wreck a much larger chunk of the transmission, whatever they didn't catch would still be clean, shorter, but perfectly secure enough to encrypt transmissions in a pinch. Right now, base stations in each linked city receive different quantum keys from the satellite, which are multiplied together and then disentangled. That system works fine, as long as the communicators trust that no secret squad of nefarious astronauts has broken into Misius itself to read the quantum key at the source. The next step toward truly perfect security, they wrote, is to distribute quantum keys from satellites via entangled photons, keys the satellites would manufacture and distribute, but never themselves be able to read. In time, the researchers wrote, they plan to launch more quantum satellites into higher orbits, satellites that will communicate with one another and with researchers on Earth in ever more complex webs. This slowly spreading, ever more practical quantum network will first be built for China and Europe, they wrote, and then on a global scale.